Good morning, everyone. I'm Bingo from National University of Singapore, and today I'm presenting our paper Scalable and Effective Page Table and TLB Management on NUMA Systems. And this is a joint work with Horizon Quantum Computing and Queen Mary University of London. So first, I will give a brief introduction of our work and then get into the details. So first, non-uniform memory access system is a way to scale the computer system's performance in the post-Moore's law era. And in NUMA systems, each CPU directly connected to a function of memory modules and forming a NUMA node. However, the NUMA nodes are connected by inter-CPU connections. And for the memory accessing in the NUMA systems, it has a huge latency and bandwidth and energy gap between local memory access and remote memory access. So here is a measurement of the memory access latency on an 8-socket machine. It shows that there is 10 times of memory access latencies in the 8-socket machine. Nowadays, the research on NUMA systems focus on ensures local data access by either place the data near to the thread or schedule the thread near to the data. And however, the critical operating system data structures are largely ignored. Most notably the page tables. So our work is focused on placing the page tables on NUMA systems. So what are the problems with page tables on NUMA system? So the first problem is page table read on NUMA system. Page table read when during address translation when the TLB miss. So the problem is the placement of page tables in current operating system is not NUMA aware. Second, the frequent remote accesses for the translation is very expensive. Even though the data is local, if the page table is not local, it's not optimal. So then, how about the page table update? So for page table update, when the page table update happen when there is memory allocation or deallocation or the application call system call to modify the page table read bit, for example, the mprotect. So once the page table update happen, there will be TLB shootdowns on all of the cores that run the process. So the TLB showdown are very expensive in the system. So we propose Hydro, the solution. Hydro automatically replicates page table entries across NUMA nodes, and it lazily replicates the page table and enables the thread locally access the page table on demand. And the benefit is it ensures the page table reads are local, and also it makes the page table updates cheap, majorly by reduce the TLB shutdowns for nodes that's with no replica. So next we get into the details. So first the basic virtual memory. Virtual memory is a way to isolate the applications and for memory management, fine granularity memory management, and it uses the page table to map the virtual address to physical address, and to reduce the footprint of page tables. The page table are usually organized with radix tree. And to read a page table from the operating system from the main memory, it needs to perform 4 to 5 memory accesses to traverse the radix tree. And this is very expensive. And to reduce the memory access page table working cost, the hardware TLB translation look ahead buffer is deployed near to the CPU core to reduce this cost. If a page table is found in TLB, then there are no page table working cost. However, the usage of TLB introduced a new problem of TLB showdown, the TLB coherence problem. So for example, here is an application, 4-thread application that runs 4 CPU cores. If CPU 0 wants to remap the virtual address VA1 from PA5 to PA8, it needs to issue TLB showdown signals from CPU core to all of the other cores that run the same process. So after the TLB showdown signal are sent, the other CPU cores need to make sure the TLB entry are flushed, and then send acknowledgement signal to the CPU 0 to make the application continuously running. So this is very expensive, and this problem becomes more than expensive on NUMA system, because the TLB showdown signal need to go through the inter CPU or inter NUMA connections, and we study this problem on NUMA system. For example, here we create a benchmark, the mprotect benchmark, which is a multi-thread application. And in this benchmark, only one thread keep modifying the page table and accessing the data, and all of the other threads are doing nothing, just spin and touch no data, which means only one thread actually access the TLB. However, as we can see from the figure, with the spinning thread number increase, the runtime keep increasing, and the performance degrades by 40 times. And this is because the increased number of TLB showdowns, as we can say. So besides the TLB showdown problem on NUMA system, the page table reads are also not optimal on NUMA system. For example, here we perform a benchmark that uses 2 sockets, and we control the placement of page table and data. And the takeaway is the page table read dominates the execution of the big data applications. And also, even if the data is local, if the page table is not local, it will significantly affect the performance. So the state-of-the-art solution, the page table replication method is proposed called MIT-OIS. And the MIT-OIS solves the problem of page table read, and it replicates the page table on every socket. So every thread on every socket can access the page table by local memory access. However, it cannot solve the problem of page table update and the TLB showdown problem on NUMA system. So we propose Hydro. Hydro is a solution that's lazy and partial and selective page table replication. For example, here is 4 thread on 4 socket, and they have each thread have its own data access and its own page table range. And if thread 3 wants to access the data on NUMA 0, the page table on NUMA 0, and it will lazily replicate the page table to node 3. And after this, thread 3 can access the page table locally on node 3. And by doing this, we solve the problem of page table read on NUMA system. Every thread can get the page table by local memory access. However, how to avoid the TLB shutdown in Hydro? Hydro has additional information like which NUMA node has what page table replications. So the environment hold show that if there are no replica of page table on a NUMA node, so the thread on this NUMA node never access the page table. So the TLB on this NUMA node never cache the page tables. So this is the insight to drive us to mitigate or reduce the TLB shutdowns in NUMA system. So here is an example. For example, we have 4 NUMA nodes here, and for the page table, it's NUMA 0 and NUMA 1 have the page table and 2 replica here. For NUMA 2 and NUMA 3, there are no replica. So here, it means the thread on NUMA 2 and NUMA 3 never access the page table. So their TLB don't have the page table entries. So here, when the core 0 wants to set TLB shutdown to other core, it's first check the replica information and avoid setting the TLB shutdown to the NUMA node that's without the replica. So here's our evaluation highlight. So first, we show the how our TLB shutdown optimization works. So we conduct experiment called munmap, and munmap, like each thread on the thread are spread on NUMA sockets, and each one is keep doing munmap and mmap and unmap. And for the baseline, when unmap or munmap happens, it will set TLB shutdown to the other socket. However, Hydro with optimization can optimize this situation, and we can see instead of slow down, Hydro can achieve 15 times speed up because reduce the TLB shutdown numbers. And also, for TLB rate, we do the experiment, the general application of data analytics. So here, we can see the Hydro can achieve the similar speed up as the best solution, the mid-OIS in page rate scenario. So, and also because when mid-OIS set up the data, it need to create create page table on every socket. So it has a page table. It needs more time to create the page table. So Hydro can improve such a situation because initially Hydro only needs to create partial page table, not the full, not the replica on every socket. And also Hydro has less memory footprint for page table. And for example, the Linux maintains 0.2 memory footprint for page table. And here is experiment on 8 socket. So mid-OIS maintains 8 times of space for the page table. but Hydro can Hydro maintains partial of the page tables on every node and maintains minimal replication. So it has a less memory footprint for page table. And to conclude, Hydro eliminates NUMA effect for both page table read and update. It can ensure local address translation, and it avoid unnecessary TLB shootdowns and optimize page table coherence performance. And it allows page table updates operations to scale on NUMA system. It also ensures minimal memory footprint of page table replicas. And it enables scalability of page table read and update to large NUMA systems. So you can find more details and the result in the paper. And thank you. Any questions?